We're now going to go through an example of computing a flux integral over a closed curve and using the corresponding version of Green's theorem in this case, which involves the divergence of the vector field f. So the curve in question is the ellipse x squared over 4 plus y squared over 9 equals 1. And the vector field we have is f of xy equals 2x in the first component and 5y in the second component. So a relatively simple vector field. The problem is to compute the flux of f through c. Now, the strict definition of the flux, and we usually use phi for flux, is it's the integral over c of f dot n ds. So, for instance, f is this vector field, and so at each point we have this vector f, and we could draw these vectors for each point on the curve. So this is just a few bad drawings of some examples. So, the vector field f is 2x and 5y. So in general, the vectors are sort of moving away from the origin. And in this case, what we really sort of mean by the flux is sort of the total amount that the vector field f is flowing through the curve C. Okay, and specifically what we mean by that is if I think about the vector n as the outward unit normal. So for each point, I have this vector n and I have my vector field f. And so when I'm really looking here at f dot n, since n is a unit vector, this is the component of the vector field f that's normal to the curve C. And then essentially I'm sort of adding that all up or totaling it up over the curve, and that's what this integral represents. So it's like it's the total perpendicular component of the vector field relative to the curve. And so it's sort of exactly the part of the vector field that's sort of flowing through the curve C. And it's pretty straightforward to use Green's theorem to show that this curve integral is equal to the double integral over the region R of the divergence of f dA. Okay, so that says that in the end we want to compute this double integral over R of the divergence of f. So the question is, what's the divergence of f? Well, in this case, because f is so simple, the divergence is quite simple. So it's equal to the partial derivative of the first component with respect to x plus the second component with respect to y. And so I get 2 plus 5. So in this case, we have a vector field with constant divergence 7. And so we just get a very simple integral here, the integral of 7 dA. Well, we could set up the bounds here, but really, we can just refer to some geometry because this is 7 times the area of R, because it's 7 times the integral of 1 dA. Now, what's the area of a ellipse where the length of the axes are 2 and 3? It's simply pi times 2 times 3. So in the end, I have 7 times 6 is 42. And so this 7 times the area is 42 pi. And so this flux integral over C, this integral f dot n ds, is equal to 42 pi because we could do a straightforward calculation of the area. Now, we could have just calculated this directly using a parameterization of C, and then we could plug that parameterization into f and compute what the normal vector should be for that parameterization. But it would have been a lot more work. And in this case, we could just use this double integral of the divergence of f, and the problem was sort of very simple. And so we got that the flux was 42 pi using Green's theorem by equating the flux integral with a double integral. And so this is just sort of another application of Green's theorem to, instead of the circulation integral f dot t ds, looking at the flux integral of f dot n ds. And again, the main benefit of the theorem is just to supplement one integral with another one that was very easy to calculate in this case.